Dear friends, welcome to yet another installment of Orbital Geek. In this video, we explore the fascinating history of modern cosmology, from the Big Bang to the steady-state theory. We discover how a horror movie inspired scientists to question the origin of the universe and how heated debates shaped our understanding of the cosmos. We examine crucial evidence, such as cosmic background radiation and the redshift of galaxies, which support the Big Bang theory. But is the case really closed? Recent alternative theories challenge our view of the universe. In the end, is the Big Bang really the best explanation for our cosmic origins? Watch until the end and discover why science never stops questioning. Don't forget to leave your comment. Which theory seems most convincing to you? One night in 1946, three professor friends from the University of Cambridge went to the cinema to watch the horror anthology film Dead of Night. This film begins with the protagonist arriving at a rural property where he finds a varied group of characters who tell their disturbing stories. After killing one of them, the protagonist wakes up from what seemed to be just a nightmare, but a phone call summons him back to the same property, thus restarting the entire story. Those three friends were professors of astronomy, mathematics, and cosmology, and the cyclical structure of that horror film inspired them to formulate one of the most credible challenges to the Big Bang theory, a theory according to which the universe is infinite, timeless, and most crucially, without a definite beginning. This is the steady-state theory of the universe. Today, the Big Bang theory is the most widely accepted explanation for the origin of our universe, but it wasn't always so. For at least 2 decades, the steady state seemed to gain more consensus. Even as recently as April of this year, 2024, new publications cast doubts on the Big Bang. But let's go step by step. What exactly does the Big Bang theory imply? Well, the theory was first formulated in 1927 as a hypothesis of the primeval atom by the Belgian physicist and astronomer, Catholic priest Georges Lemaître. The Big Bang label only became popular in 1949. Ironically, this was intended as a slightly derogatory phrase and was coined by one of the founders of the steady-state theory, English astronomer Fred Hoyle. We'll get to him later, but for now, let's focus on Lemaître. According to his hypothesis, the universe originated from a single point, infinitely hot and dense, about 13.7 billion years ago. A sudden explosive expansion occurred, inflating the primeval atom faster than the speed of light. According to physicist Alan Guth, this phase lasted a fraction of a second, to be precise, 10 to the power of minus 32 of a second. After this initial inflation, a second phase known as reheating began. This was the process by which radiation and particles began to populate the universe. In the next phase, around 380,000 years after the initial bang, free electrons floating in the vacuum began to aggregate with protons and neutrons, thus forming the first atoms. This process can also be described as a transition from a plasma state of matter to a neutral gas. According to NASA researchers, this process allowed photons to permeate through the initial chaotic soup of the universe. Now, photons are the most elementary particle of electromagnetic radiation, such as light, and this primordial light shining through our primitive universe has been described as the residual glow of the Big Bang, or more appropriately, as the cosmic microwave background radiation, or CMB. From that moment on, the universe has been basically fine for billions of years. Crucially, it has never stopped expanding since that first incredibly fast and incredibly violent explosion. This is a key aspect of the primeval atom or Big Bang theory. We live in a constantly expanding cosmos, stretching at a measurable rate from the primordial point of origin. The theory first proposed in 1927 by Father Lemaître is now mainstream, but for much of the first half of the 20th century, it was actually the exception. Before and immediately after that year, models based on continuous creation were in vogue. Now this point was quite complex for our tiny brains, so let us clarify. According to the Big Bang theory, all matter currently present in the universe was contained within that incomprehensibly dense primordial point. On the other hand, continuous creation models maintain that matter is constantly created from radiation, and this new matter replaces old matter that turns into energy in stellar processes. So, new matter comes in, replaces old matter. The overall result is that the universe remains in a steady state. American physicist William Macmillan was the first to propose such a steady-state model in 1918. 10 years later, his colleague James Jeans speculated that matter was continuously created at the center of spiral nebulae, where matter is poured into our universe from some other spatial dimension, so that they appear as points where matter is continuously created. Even Albert Einstein was one of the early proponents of steady-state models, as discovered by a team of researchers from the Waterford Institute of Technology, the Dublin Institute for Advanced Studies, and the University of Cambridge. The researchers examined an unpublished 4-page manuscript written by Einstein in 1931 and titled "On the Cosmological Problem." In his paper, the famous scientist proposed a mechanism to explain how the density of matter remains constant, even as the radius of the universe continues to expand. Einstein concluded that new matter was continuously formed from empty space, a process that also determines the expansion of our universe. Without going into specific details, which would be totally beyond our understanding anyway, the research team identified some flaws in the equations written by Einstein to prove his steady-state model. Their conclusion was that, quoting, "Einstein discovered the error at a later point, realized that the model led to a trivial solution, and set the work aside without correcting the equation." In addition to these precedents, what is now referred to as the steady-state theory was formally developed by Cambridge professors Fred Hoyle, Hermann Bondi, and Thomas Gold. These are the three friends from the beginning of our episode who enjoyed an exciting night at the cinema. Upon returning home from the cinema, Gold suggested producing a film with a cyclical structure similar to Dead of Night, so that a viewer could start watching it at any point. He then expanded his thinking to the entire universe. Could it be that the universe was like his hypothetical film, an endless cyclic roll, without beginning and without end? More precisely, Gold wondered if the universe, as it expanded, was being replenished with newly formed matter. Fred Hoyle elaborated a set of complex calculations that suggested that matter could indeed be created continuously, and if matter was really being created everywhere all the time, this meant that the universe would have to expand to make room for it. So, let's break this down, okay? The fact that the universe is constantly expanding has been widely publicized since 1929, when American astronomer Edwin Hubble published his eponymous Hubble's Law. According to Hubble's observation, galaxies are moving away from Earth at a speed proportional to their distance. The more distant the galaxy, the faster the speed. This law implies that the average distance between galaxies is increasing. The universe, therefore, must be expanding over time. Hoyle, Bondi, and Gold brought a new assumption to the picture: the continuous creation of new matter at the small rate of 1 hydrogen atom per 6 cubic kilometers of space per year. The cosmos seems pretty stingy if you ask me, but according to our trio of movie-loving professors, this rate is actually enough to form new stars and galaxies. To recap then, the two essential ingredients of this theory are: 1. New matter is constantly being created. 2. The universe is constantly expanding. So, creation and expansion. This doesn't sound exactly like a steady state, does it? Well, the point is that Hoyle, Bondi, and Gold were thinking about the average density of matter. Once again, if new matter constantly enters a constantly expanding universe, the average density of matter in the cosmos will remain constant. Therefore, their model describes the universe as being in a steady state. Another important element of this theory is that the universe, although expanding, is stationary on a large scale. This is known as the perfect cosmological principle, according to which the universe is infinite in size, infinitely old, and destined for an infinite future. And at this point you might be thinking, but what about the creation of new matter as Hoyle demonstrated? What about the birth of new stars and the evolution of planets? In reality, the steady-state theory admits that changes can occur, but only on a very small and localized scale. But as new matter is created, old matter disappears into nothingness. As stars explode into life, old stars deplete their fuel and stop shining. So, if we look at a large region of space, some tens of millions of light-years in extent, we can perceive that the average amount of light emitted by stars does not vary over time. Once again, this leads us to the conclusion that the cosmos is endless, homogeneous, and timeless. It is the same in all directions and does not evolve over time. This concept is clearly in antithesis with the primeval atom hypothesis, or Big Bang, which identifies a clear point in space and time when the universe exploded into existence. The big question is, did the steady-state theory make sense? I hope I'm not giving too many spoilers here, but despite the initial popularity of the steady-state theory, eventually the Big Bang came out victorious. The first blows against the steady state came courtesy of radio telescope observations in the early 1960s. These observations proved the existence of a large number of radio sources at a distance of billions of light years. This led to two conclusions. First, those sources had emitted their signals billions of years ago, and second, billions of years ago, there were more radio sources than there are now. This latter conclusion implies that the universe is changing in more than just a small and localized scale, which in itself contradicts the steady-state theory. Furthermore, in 1963, astronomer Martin Schmidt discovered a new class of celestial bodies up to 1,000 times brighter than the Milky Way, but much smaller. Astronomers would later recognize these objects as quasars. Now, quasars are found only at enormous distances from Earth, which implies that the light we see today was actually emitted billions of years ago. Therefore, the fact that quasars only existed billions of years ago provides more evidence that the universe has changed over time. The steady-state theory suffered another blow in 1965, thanks to an accidental discovery by two engineers working for Bell Telephone Laboratories, Arno Penzias and Robert Wilson. One of their radio receivers picked up some anomalous data, which Princeton University researcher Robert Dicker identified as evidence of the CMB, the cosmic microwave background radiation. To simplify, Penzias, Wilson, and Deke had picked up the faint background echo left by the initial stages of the primordial Big Bang. The existence of the CMB corroborates Lemaître's hypothesis, but cannot be explained by the proponents of the steady state. But they tried, arguing that this type of radiation was emitted by one or more supernovas. Extensive research on the CMB proved that it was equal in any direction of the universe, and therefore could not have been emitted by several scattered supernovas. Subsequent research piled up even more in favor of Team Lemaître. Take the abundance of light elements such as helium, isotopes, and lithium, for example. These were likely formed in the very hot and very dense first minutes after the Big Bang. And finally, we have to take into account the Doppler effect. This fundamental principle explains how perceived changes in the frequency of light, sound, or other waves depend on how a source and an object move towards each other. This effect influences the light emitted by celestial bodies. If a star or planet is moving away from us, its light moves towards longer wavelengths. In scientific jargon, the body is said to be redshifting. On the other hand, if a celestial body is moving towards us observers, its light waves appear shortened. In this case, the body is blue shifting. Measurements of the light emitted by stars have shown so far that all galaxies are redshifting, that is, they are moving away from us. This observation further confirms the Big Bang theory, as it shows that our universe is in a constant state of expansion. Eventually, Hoyle, Bondi, and Gould's theory gradually fell out of favor among cosmologists as more and more evidence supported Lemaître's initial hypothesis. As Stephen Hawking once described the steady state theory was what Karl Popper would call a good scientific theory. It made definite predictions that could be tested by observation and possibly falsified. Unfortunately for the theory, they were falsified. You would be forgiven for thinking that the matter is settled. The observable cosmos has a definite point of origin and has been constantly expanding since then. But, unfortunately, not everyone agrees with the established academy. An article by science writer Stav Dimitropoulos, published by Popular Mechanics in April 2024, drew attention to a 2022 article by Jack Willenichik, writing for Progress in Physics, which claims that the Big Bang may be a fraud. Willenichik himself is quoted saying, "No, the universe did not begin as an exploding atom or anything like that. There is no beginning or end to the universe." Now, we must specify here that Mr. Willenichik is an amateur astronomer and lawyer by profession, but it seems he did his homework. Willenichik thoroughly examined the Big Bang theory and claimed that its weak point is its reliance on the Doppler effect as a means to prove it. According to him, The Doppler effect is a 180-year-old theory that no one has backed up with experimental evidence. Therefore, Lemaître very much doubts that celestial bodies can be redshifting. In fact, he doubts whether a redshift is indicative of motion at all. The author of the article based his observations on a spectroscopy test first used by astronomer William Huggins in 1868. To clarify, spectroscopy is the measurement of spectra, that is, the intensity of light emitted by celestial bodies. He then asked a professional astrophysicist to process spectrometry data provided by the Keck Observatory in Hawaii. According to Lemaître, the result of his studies is aligned with the cosmological model known as the tired light model, itself incompatible with the Big Bang. Tired light was first conceived by Swiss astronomer Fritz Zwicky in 1929, who attributed the redshift of the universe to photons losing energy as they travel through the cosmos. Therefore, the phenomenon of redshift is not due to motion, but rather to energy loss. Thus, Lemaître concluded that the universe is not expanding, but static. The author attacked the Big Bang theory and the Doppler effect also from another angle, citing Isaac Newton's corpuscular theory of light. According to this theory, light is made of corpuscles, or small particles traveling in a straight line. These corpuscles come in different sizes, with the larger ones emitting blue light, while the smaller ones radiate red light. Adhering to this theory, Lemaître challenges the fact that different color shifts depend on the wavelength of light emitted by a celestial body. In fact, the author rejects the idea that light must be a wave. In his own words, if light is not in waves, then there goes the Doppler theory, because the whole theory is based on the idea that light is in waves. Popular Mechanics asked university physics professor Stephen Hawley to review Jack Lemaître's article. His verdict: the premise that the Big Bang is a big fraud due to its reliance on the Doppler effect is a big leap in logic. Doppler's theory has been repeatedly tested and has held up. Professor Hawley further argued that without relying on the Doppler effect, we would not have been able to engage in extraterrestrial exploration. Quoting again, "We have been able to reconcile the chemical composition of stars and planets by noting the correspondence of spectral lines with known lines observed from chemicals on Earth through Doppler spectroscopy." Hawley concluded by admitting that science may never have a 100% conclusive proof that the Big Bang theory is correct. However, it is our best cosmological model for describing the origins of the universe, corroborated by decades of observations. Quoting again, "We don't live in a world of alternative facts. We must go where the evidence points. There is nothing to suggest that the Big Bang is a myth at this time." Once again, you would be forgiven for thinking that the Big Bang versus steady-state matter is settled once and for all. Well, maybe it is, until a new hypothesis emerges. And by the way, should we be grateful that the debate is settled, or should we be grateful for the fact that there has been an ongoing debate? To conclude, we would like to borrow some words and some thoughts from Yuri Balashov, professor of philosophy at the University of Georgia in the United States. In a 1994 article, he argued that cosmology as a whole gained from this controversy. The initial success of the steady-state theory, in fact, stimulated research in the fields of stellar nuclear synthesis and radio astronomy. Both fields of research, especially radio astronomy, eventually contributed to refuting the steady state and propelled science towards confirming the Big Bang model of the universe. In Balashov's own words again, "It is not obvious that these and some other achievements would have been made so quickly if there had not been a steady-state theory to be defeated." And that's the beauty of science. No hypothesis is conclusively wrong, nor conclusively true until it is proven or refuted by evidence. No matter how outlandish, no matter how subject to being discredited, each new hypothesis, each new theory, concept or model is another log thrown onto the bonfire of scientific debate, a fire whose flames have propelled our earthly minds, and even our bodies, ever closer to the secrets of the universe. A century of cosmic debates, crazy theories, and scientists arguing like teenagers on Twitter. The Big Bang still reigns supreme, but don't be fooled. Science is a dramatic diva who loves an unexpected twist. Who knows? Tomorrow we might discover that the universe is actually a computer simulation running on a bored alien teenager's laptop. The fact is that for now, the Big Bang is our best bet. But hey, science isn't about absolute certainties. It's about questioning, testing, and occasionally shouting, "Eureka!" in the shower. So, let me provoke you with this bombshell. If we could time travel and witness the beginning of the universe, would we see a cosmic explosion, or just Fred Hoyle laughing at all of us? Share your crazy theory in the comments.